Hi, I've been asked to provide some more background on logarithms because there wasn't much in the first module about it. So um, what we'll do is I'll just give you a very brief overview of the background and context of them because it helps if you understand what that is, because that way they make a lot more sense. Now, the mathematics for them wasn't actually developed until the late 1500s, and it was developed by a couple of different people, Napier being one. That was the two gentlemen in the front screen. Now, the primary idea at the time was to provide a method of doing multiplication and divisions. For them it was very large numbers, but you can also do it with very small numbers. Now, if you have a problem like this, the big issue is huge numbers and it's very messy and very easy to make mistakes. So what they're trying to do is to simplify the mathematics involved. So essentially they invented logs, and what it does, it makes a messy situation easy, because what it does is it reduces multiplication down to addition. Now what we'll look at first is how that works, but keep in mind when it's used for that purpose back in those days, it was only ever going to give approximate answers. It wasn't accurate, but it didn't need to be because of the size of the numbers anyway. Now if you had a problem like the one we just had, what you could do is to consider it like this. The first number, 345,453,000 and so on, if you rewrite it, it actually, as a power with a base of 10, it's 10 to the 8.5 whatever. The second number is 10 to the 5.108 and so on. If I'm going to multiply those two numbers though, what this does is when you multiply powers with the same base, you add the indexes. So long as I can get the numbers into the power form easily, it reduces a difficult multiplication problem to adding 8.5 something to 5.1086. So it reduces it to an addition. The hard part at the end, of course, though, is I've now got to get back from 10 to the 13.647 to an answer, or what that actually means as a number. So what they did to make life easy was they produced tables which presented the steps at the start and at the end. That is, transferring a number into a power. At that time it was of 10, and then at the end converting the power of 10 back to a number. So you didn't actually have to do anything except look up some numbers, add a couple of numbers together, and then look up the table again to get the result. So very straightforward process, quite clever in my view. So what we have to do now is to look at it in a contemporary sense. We want to understand, first of all, what is the relationship between logs and powers. Let's consider the power way of representing the problem. It would look something like that. If you were thinking about it as logs, what you would write it as is something like this. You have the original problem and you just get the logs of the things involved, and what you end up with is an addition problem. At the end they used to call it the anti-log. The log was getting the, notice here, that number there and that number there are the indexes from the line above it up there. So getting the log of something, essentially what you were doing, you would look up the tables and you would get the index for the power of 10, and then you would write them down. You would then add them together to get a value, and then you would do what they called anti-logging. And essentially what anti-logging does is you will look up the appropriate table and it takes that which is an index of 10, that's actually, you're trying to work out 10 to that index, and you would get back to the original, the number that is the answer to the problem, right? So it's a fairly straightforward process in theory, and it wasn't that hard in practical. I had to do these when I was actually in high school, and I'd do that sort of a problem. Now, in reality, the tables only went to 4 decimal places, so the numbers you were adding together weren't really all that big, and there weren't that many numbers in them anyway. Now, let's consider the comparison between a power representation and a log representation. Now, we all know 100 is 10 squared, 10 by 10. If I write that as a log equivalent, what you have is that the log of 100 is 2. That is, when I read the log of 100 when it's to base 10, the way I think of it is, what power does 10 have to be raised to get back to 100? And the answer, of course, is 2. 10 to the 2 is 100. So those two statements are actually saying exactly the same thing. So anytime you see a log statement, it is in fact simply a power statement, but just using a slightly different way of representing what it is. Now, consider something like, what's the log of 54? The way you read that is you're asking yourself, to what index do I have to raise 10 to get the answer 54? So, writing it as a problem, it would look something like that. Notice here, if we read that, we have, there's the base of 10. What is the number that I index that I have to raise 10 to get 54? So any log statement like that has an equivalent power statement that you can make. Now, logs, obviously in maths now with computers and that sort of thing, that use for logs is just completely out of vogue. We don't need it anymore. But logs have a particular use which is very handy in mathematics. Consider if you've got an equation like 54 equals 10 to the x. Generally, if you had a problem like that one, 54 is x to the 10, you can work out what x is quite easily by getting the 10th root of both sides. When x is the base of the power, it's an easy problem to do. But when x is the index, somehow you've got to get x out of the index, and that's where logs come in. Because what we do is we get the log of both sides of the equation. Now, the place to look of particular interest is that there. If I have the log of 10 to the x, what that reduces to is just x. Because the power of 10, having a power 10 to the x and then getting the log of it is like squaring something and then getting the square root of it. One is the opposite of the other. So therefore, getting the log of both sides like this allows me to get the x out of the index and down to the bottom. Looking up the log of 54 is easy, just put it in your calculator, it's 1.73. So the answer to that is a one-line problem. You just get the log of both sides, look up the log of 54 on a calculator, and that's the answer. So very straightforward, but that there is a very important use for logs in mathematics. Now, let's consider a problem like this one. This is just some straight algebra. We're trying to find out what x is. Notice it's in the index, so you automatically know you're going to have to use logs at some point. Now the key is you don't use logs until you've got that part sitting on its own on one side. So we'll move the 5 first. So we have the power there on its own. Once you get to a single power like that, that's when you can then start getting logs. So we get the log of both sides. Log 17 is the log of 10 to the 2x plus 3. And because of that there, now reduces to 2x plus 3 because these two cancel each other out. They're the reverse of each other. So then we have reduced at this point here. We now have an ordinary linear equation which we know how to solve. Take the 3 across, take the 2 across, and you get an answer. Let's consider that one. Exactly the same problem. We know we've got a power on the right-hand side. Oh, I changed the A. The A should be a 10, don't worry about that. But if you get the log of both sides over here, what you get on the right-hand side is the log removes the power of 10 and you just get with x squared, and then you can proceed with that as you would normally. Get the square root of both sides and it's plus and minus. Typical sort of thing you've seen before. Now, up to this point, we've only worked with the power, the log using base 10 as a power of 10, but you can, in fact, use any power at all, any base. There are two that are most commonly used, though. They are 10 and this number called e. Now, if you want more on what e is about, go to that website and it talks to, it's actually Euler's number, and it tells you the background of where it came from. But it's a very important number because it's like pi. It comes up in a variety of everyday, natural, real-world situations, which is why we use a lot. It's also why, when we work with it in logs, it's called the natural log, because it arises naturally in everyday problems. Now, one example it is used in is population modelling, which I'll show you in a short time. Now, the equation I've got there, P0 e to the RT, is called the population equation, and it's actually used to model the growth in populations when you don't have things like predation and stuff like that. If you've got predation or other factors that are influencing what's happening in the natural situation, obviously that's the starting point we've got here. In this case, P on the left is the final population, P0 is the initial population, R is the rate of growth as a percentage, and it's expressed as a decimal, and T is the time. Obviously you have to be consistent in your, for rate of growth and time, you have to be consistent in the time unit. So the rate of growth is something per year, time will also be in years. So just to give you a couple of examples of how this might actually be used in a real world problem, consider if in 1950 the world's population was 2,555,982,611. If the growth rate per year is 1.6%, what's the population in 1955? So modelling this, we know it's a population problem, so we know that P0, which is the initial population, is the 2,555,000,000 one. The rate of 1.6% is 0.0168 as a decimal, and the time is 5 years because it's going from 1950 to 1955. So if we substitute them in the population equation, we get the second line there. You put that in your calculator and you get 2,779,000,000 and so on. A rather more practical use of logs is what is this problem. If I had a similar sort of situation, I had the same starting population and the same rate of growth, but what I actually wanted to know is, when is the population going to be 3 billion? So I can look forward into the future to work out how many people are going to be around at a given point in time. If I do the substitution this time, what I end up with is that the time, because the thing I don't know is the time, I end up with that term there where my unknown variable is in the index. So as you can see, I've transposed the 2.5 billion over to that side, divided. We then get left on the right-hand side with the power. Because it's to base E, the way I get rid of that is to get the natural log, which we represent with the letters ln. If you use just log with no base on it, it means to the base 10. If you use ln, it means to base E. So applying the natural log to that gets rid of it, and we just end up with a nice simple equation. 0.16 is 0.0168 t, and t comes out to be 9.52 years. So you can see that the problem works. Logs aren't that difficult to use, but it helps if you understand the nature of their relationship with powers and indexes and bases. It works a lot better. Talk soon.